clear, so you can see kind of what's going on. If it's too messy, do let me know, and I'll try and make it neater. Although like I said, I'm not very good with this writing pad thing, but I'm going to try my best. So today, Dr. Mirsani asked me to review kind of the circuit analysis again. So it's going to be very similar. If someone has their mic on, could you mute it? Because I'm getting a feedback. It'd just be easier for everyone to have them mute. She asked me to go over it. It's going to be very similar to what we did at the beginning of Electronics 1, but it's just a review of circuit analysis and stuff like that. So we're going to be going through KCL, KVL, mesh analysis, nodal analysis, that kind of stuff. So it should be helpful for the skills you'll need for the other things that we'll be doing in Electronics 2. Okay, so we have this circuit here. We have independent current sources here at 5 and 10 amp, and we have resistors here at 2, 6, and 4 ohms. We want to find V1 and V2. So what we're going to do is this is going to be a type of nodal analysis, so to speak, but we're going to be using the KCL, the current laws. So what we're going to do is we're going to sum up the currents that enter into each of these nodes, and we're going to collect some equations so we can collect these variables. The first one we're going to do is we're going to do a KCL right here at node number 1. So it's going to be 1, and this is going to be 2 for our equations. So first thing is we're going to do a KCL. We're going to do it at 1. What that gives us is that gives us entering, I see 5 amps. And depending on how you want to define it, I don't know why that keeps popping up, but depending on how you want to define it, you can say that this current is exiting. I think that's fair because we're going towards ground. And for the purpose of my analysis, I said the current's going this way. If I end up being wrong, we'll just end up with a negative value for that current, and then it'll work itself out so long as we remain consistent with how we assume. If we assume that it's going this way in the first analysis, we have to assume it's going this way when we do this node as well. So that's just an important note. As long as we're consistent, it doesn't matter if we're right or wrong. So I'm going to say that 5 enters, and what exits is the current going through the 2 ohm resistor and the current going through the 4 ohm resistor. Now, what are those currents? We know that the current is high potential, or flows from high to low potential. So we're going to say the first one here, the 4 amp, is going to go flow from high to low. So we're going to say V2 minus V1. So for this one here, or V1 minus V2, excuse me, and it's going to be divided by the resistance. That's how we get the current. For the other one, again, from high to low. So V1 to ground, which is 0. And divided by the resistance 2 ohm. Okay. Now, I'm going to do a couple math steps here. I'm going to multiply by 4 to get rid of the denominators here in these fractions. So we end up with 20 equals 2V1 plus V1 minus V2. And scrolling down, if I can. One second, I will find it. I guess that'll be the way we scroll down.
Could you go back for like 1 second?
Sure.
Thank you.
So I'll just finish off that equation now that I have enough room. Our first equation we're going to end up with from node 1 is the following. Like I said, guys, I apologize. I'm not very good with this writing pad thing, so it's going to be really kind of choppy, my writing. And apparently this thing's going to keep popping up on me. I'll have to figure out what I'm doing wrong. Okay, so then we have here let's see what I can do here. Okay, so then we end up with 20 equals 3v1 minus v2. So that's our first equation. Now, if we go back up to here, we have node 2. We can also do KCL there. We can sum the currents entering and exiting there. So if we do KCL at 2, I'll just do it right here so we can keep the circuit in view. KCL at 2. Going back up to the circuit, we see we have this one. We have to define it as entering because that's what we defined in the first one. Like I said, we have to remain consistent. This one here is told to us it's exiting. We have this one here entering, that's told to us. And then I'm going to say that this one exits, just because I think that's fair. And again, it doesn't really matter. So I'm going to define it going this way. So when we do that, we have 10 entering. We have the current across the 4 ohm resistor entering, which from the first part we found was V1 minus okay. It was V1 minus V2 divided by 4. See if I can get rid of some of the things that keep appearing on me. Okay, so we had 10 minus V1 minus V2 over 4, or 10, sorry, plus the quantity V1 minus V2 over 4, so that current, and that's equal to what's exiting. So what's exiting? We have 5. Now that is an interesting feature. So what is exiting is the 5 and then the current across the 6 ohm. Five plus V2 minus 0 over 6. Then, when we solve this up, again, it's a couple math steps, just getting rid of the denominators, multiplying by 6, I end up with the following. 60 equals 2 V2 minus 3 V1 plus 3 V2. And then when I simplify all of that, 60 equals 5 V2 minus 3 V1. And that's going to be equation 2. So right now, I've collected 2 equations using KCL. I have 2 equations, and I have 2 unknown variables, V1 and V2. So I'm ready to solve. So solving, I can just do actually the sum of the 2 equations because we have a positive and a negative V1. So if I do equation 1 plus equation 2, I end up with this. 80 equals 4 V2, which means V2 is 20 volts. Okay, and if V2 is 20 volts, I can put it into this equation right here. It doesn't really matter which one. And then if I put it into 2, I end up with 60 equals 100 minus 3V1, which means that we end up with V1 is 13.3 repeated volts. Any questions on how I solved that? I hope the writing is clear. Is the writing, can everybody see the writing? Okay, like I know it's going up and down all over the place. Scroll up.
Alex, can you please zoom out a little bit?
That I can do.
Thank you.
Oh, okay, let me try that again. I accidentally closed the tab. Be up in 1 second. Well, okay, there we go. And zoom out. Share. How's that? Can you see it better?
Yep, that's better. Thank you.
No problem. Oh, that's cool. Okay. Let's try that again because I think the share went wrong there. Okay. So now to question 2. Now for question 2, we've got another circuit. This time we're going to do is a similar analysis, except we have a couple of dependent sources. So we're going to talk about how to handle those. So we have this circuit right here. Okay, so that keeps appearing. Not sure why. Okay, so we have a 4 ohm here, 2 ohm, 8 ohms, 4 ohm. This here is dependent on a current called IX. And then IX is the current here that flows through that 2 ohm resistor up there. And then this is an independent source at 3 amps. So we have V1, V2, so node at node 2 voltage, and then 3. So we want to find each of those. Again, we're finding the node voltages V1, V2, and V3. So the same approach, because we're finding voltages, we can do a nodal analysis. So the first step, I'm going to do KCL at each of the 3 nodes, and then that should collect enough equations with the 3 unknowns, and we should be good to go. So what's happening there? We have a bunch of currents at this node. We have, first of all, IX is leaving, 3 amp is entering. Now, depending on what you want to do, we can define it any way. I'm going to say that the current flows out. No particular reason. I just called it that way. And again, like I said, it doesn't matter as long as we're consistent. So the only thing entering based on the assumptions will be 3 entering. And then we have IX plus the voltage going, or the current going across or through this resistor here, which is going to be V1 minus V3 divided by 4. So what is Ix? Ix, again, can be written in terms of the node voltages. So you have Ix is actually equal to V1 minus V2 divided by 2. I'd redraw bigger? Sure, I can definitely do my best. I'll draw it again. Okay, I'll have to figure out why that keeps popping up. So I'll try and draw bigger. So we have, first of all, 3 amps. Four ohms, 2 ohms, 8 ohms, 2 times Ix, and this here is Ix. Okay. So then we have this. Like I said, Ix is actually this current here, and it can be defined using the voltage, or the nodal voltages 1 and 2. So I'm going to sub that in for this equation right here. Ix is V1 minus V2 over 2 plus V1 minus V3 over 4. Okay. And then after a math step, which is just going to be multiplying by 4 and then factoring in all that, I end up with the following. 12 equals 3V1 minus 2V2 minus V3. So I just multiplied by 4 and then collected the like terms. So it's 12. Okay. So now, I'm going to scroll a little bit down here. Make some scrolling room here. Don't know if this is the official way to do it, but it's the way that I found. Okay, so now we're going to look at node 2 and do a KCL there. So we see here, KCL at 2. Okay, so what's going on at 2? We have Ix entering. I'm going to say that this one goes down. That's just my opinion. And then I'm also going to say that I think this one is exiting. Again, I stress it really doesn't matter. It's just kind of preference. So I'm going to say here that Ix enters, and we know that Ix V1 minus V2 over 2, so that enters. And then what's exiting? We have V2 over 4 going that way. And then we have V2 minus V3 over 8 as well. Now, I'm going to do a math step again. All I'm going to do is I'm going to multiply by 8 to get rid of the denominators and then do some collecting of the terms. So then we end up with equation 2, which is 0 equals negative 4 times V1 plus 7 V2 minus V3. Yep, I'll scroll back up. It just kind of put me there. Okay, so now third is KCl at the third node. Now remember, we decided that the current going to the top branch was going this way. So we have to maintain that assumption when we go into here. So that has to be entering. This one we said was going this way, so that's also entering. And this one is also entering. I know physically that doesn't make sense, that everything should enter. I'm sorry, it's not actually all entering. That's why it doesn't make sense. Because this one here, I drew the direction wrong. My apologies. So it is, in fact, a dependent source, so it's going to be the diagonal box, but it's going down. Okay, so then that's the only thing that's exiting. The other two are entering based on the assumptions we made. So we end up with what's exiting, which is 2 times Ix. 2 times Ix, and that's equal to V1 minus V3 over 4 plus V2 minus V3 over 8. And we know what Ix is. We know that Ix is V1 minus V2 over 2. So then we're going to end up with V1 minus... I don't know why it thinks I want to go all the way to the bottom. So V1 minus V2 is equal to V1 minus V3 over 4 plus V2 minus V3 over 8. And now again, just doing some factoring and some math, I end up with this equation for my third equation. 2V1 V2 plus V3. Okay. I'll go back up. It keeps putting me towards the bottom of the screen. I'm not sure why, and this window keeps popping up. Okay. So I have 3 equations now, and I have 3 unknown variables, so I can go into the solving steps. What I'm going to do is, if you guys can see these equations clear enough, I'll leave the solving steps for you, and then what I'll do is I'll just give you what the final answers are. When I solved them, I got V1 to be 4. Okay, so it thinks that I want to write there. I don't know why. V1 was equal to 4 point... 4 point... Okay. I guess this is my punishment for buying the cheap one on Amazon. All right. I will get back to the bottom of that. Okay, 4.8 volts. V2 is equal to 2.4 volts. And then V3, I solved it to be negative 2.4 volts. So those are the 3 solutions, and again, we have the 3 equations we need. Are there any questions? Okay. If everyone's ready to move on, I'll move to the next one. Is everybody okay? Okay. So our next question is going to be now, I've got another one with nodal analysis, but what I'm going to do is I'm going to skip that and we're going to get into mesh analysis, or actually we're going to use mesh analysis. No, I think we'll do a supernode next. So we'll talk a little bit about supernodes now, just to review that, and we'll skip the next one, which was another nodal analysis. Nodal analysis, as you guys kind of saw last semester, that kind of the current laws and stuff like that are really important for when you're solving transistor problems. So that's why I kind of emphasized it in the questions I picked. Okay, so our next circuit, let's see how this goes. Our next circuit looks like this. Okay, so there's okay, minus plus. Again, I do apologize for the messiness and this constant appearance of extra windows and the thing moving up and down. I don't know why it's doing that. I'll have to see if it's a driver issue. Okay. 10 ohms there. This here is a 2-volt source. Not that that looked like a 2 at all. Two volt. This is 2 as well. Oh, ohms. And then this one here is 4. We have 7 amps in the independent source there. 2 amps. And a connection there. Okay, so with this one here, we have V1 and V2 at these nodes right here. So we're still solving the nodes. However, we have what's called a supernode. The supernode is just, we can treat this here when we do current analysis all as one node. Because if you look, there's this current here is going to be if you do it for individually, you don't know how to find this current in the middle branch across the voltage source. So what we do is we treat it all as one, because the only difference is really this current here, but it flows from here to here, and it will cancel out in the analysis. And then that way we can avoid having to deal with this this branch here where we don't have a way of determining the current through our analysis. So that's how we're going to make it a little easier, is we're going to consider it all as one node, which is called a supernode. I'm not even going to bother trying to circle it because I don't think that's going to work out with this current writing pad. So you're going to have to take my word that it's this here. I hope, can everyone see that I'm hovering? I hope. Okay, so what I'm going to do at the supernode, I'm going to do KCL. At supernode. So what do we have here? We have 2 amps, that is entering. We have this here, I'm going to say it's leaving, just because. I'm going to say this one's leaving too. I usually like to define them as going towards ground. I could be wrong, because if the voltages are negative, it would actually be flowing from ground, because ground is 0. And again, we go from high to low. This here is exiting. We're going to solve for the voltages here and here. So nodal voltage is V1 and V2. the first step that we have to collect equations, and the way we're going to collect them is using a supernode. So we'll get a KCL equation, and then we're going to go, we'll see what we need and what we can do to get more information. The first thing is just to see where the currents go for the KCL. So it's all considering this. This here, we don't count, and the reason we don't count it is because it enters and exits the supernode. So it's not contributing to the net in or out. So here we have entering 2, we have leaving all of these. So 2 is entering. I don't know why it thinks I want to write there. Entering here. So this one here is V1 minus 0 divided by 2. So V1 over 2. This one here, V2 over 4. And then 7. Again, we just do a math step. I'm going to multiply by 4, get rid of the denominators, and then we end up with equation 1, which is the following. V2 equals negative 2V1 minus 20. I will try to circle it. I will do it. Okay, I'm going to grab red. I'm going to do it in a dot because that seems to work better. Because, like, I don't know if you guys can see the pop-ups that keep happening to me. It keeps popping up with ideas on how to write. Could be me doing it wrong. But yeah, the supernode is there. That's the supernode. So it incorporates node 1 and 2 and the 2-volt source. Okay, so we have, using KCL at the supernode, so considering all the currents entering and exiting from both of the nodes there, we end up with equation 1 here. But we have 2 unknown variables, which is a problem. So the problem is that we need 2 equations if we want to solve a linear system here with 2 unknown variables. So where are we going to get the second one from? We can't really do KCL because there's no valid node to give us any information. We've used them all. However, we can do KVL, the voltage laws, the Kirchhoff voltage laws. So what we're going to do is in the center, we're going to do a voltage loop. Because remember, the sum of all the voltages in a loop is 0. So at the center loop, we're going to do KVL. Center loop. Okay. So let's go and see what we got here. We have V1, we have V2, we have a 2-volt source. Okay. All well and good. Remember, V1 is the voltage across this resistor because it's V1 minus 0 is the drop. So V1 is the drop. V2 minus 0 is the drop. So V2. Now remember what I said in the very beginning. We've assumed the directions of the currents. That also implies the direction of the voltage. So when we do our loop going through, we have to keep that consistent as well. So what we're going to do is we see here if we're going in a clockwise direction, so clockwise means that we are going opposite or in opposition to the current flow that we've defined for V1. That means V1 is negative in our loop. So we say 0 is the sum. Okay, 0 is the sum. Negative V1. Why? Because we're going in opposition to the current flow that we've defined for V1. It's also negative 2 because we're entering the negative terminal. If we go clockwise, we're entering the negative terminal of the voltage source. So minus 2. But we're following the direction that we've defined for V2. So it's going to be positive V2. Okay? And what does that tell us? That tells us that, excuse me, I'm not going to waste a step on that. So what I'm going to do is I'm just going to go direct. So we have an expression for V2. I'm just going to make an expression for V1. If it will let me. So V1, in this case, is going to be equal to V2 minus 2. Fair enough? Oh, well and good. Now I can just sub them into each other. I can put equation 2 into equation 1, and then I can solve that way, because I've got two equations, two unknowns. And when I do the math steps, I'm going to end up with V1 is negative 7 1/3 volts, which is negative 7 3 repeated volts. And then V2 ends up with negative 5.3 repeated volts. Now, if you'll notice, they are 2 volts apart, which is kind of what we use that KVL to tell us, right? We could have done it kind of almost by intuition because we see that there's a 2-volt source, but formally with the KVL is more secure, so we know that we're doing it 100% correct, and that we're satisfying all the circuit theory laws that we know. Does that make sense? But basically, the only information we get from the KVL is that they are 2 volts apart, which kind of we see on the schematic, right? Because there's a 2-volt source between them. But we follow the rules and make sure all the laws are satisfied. It's a much more formal solution. Are there any questions?
Hey, Alex, can you go through how you did the KVL again?
Sure, for sure. So the KVL, I'm going to do my best to draw. So bear with me again. I'm going to draw it in blue. So what I did was I did KVL in the center loop here. So I went like this. Okay. It's almost drawn. I went this way. So you see there's kind of like a circle with an arrow. It's poorly drawn, but you get the idea. So what happened was, when I do KVL, KVL states that in any closed loop, the sum of the voltage is 0. So that means in this closed circular loop here in the middle, the sum of the voltages must be 0. What are the voltages? There's a voltage drop across this resistor right here, the 2 ohm. There's a voltage drop across the 4. And there is this voltage source right here. There's 3 pieces, 3 voltage, almost like 3 voltages we can consider either as drops or sources. When I do the KVL in this direction, so going that way, what I see is that I see that we've defined current going this way for both of them. When I go this way, I'm going against the current, see, in my rotation. And I'm going with the current at this part of the loop. So this one here, this drop here is V1 across this resistor. That's negative because it's going in the opposite direction of the current that we had defined direction, for which we defined direction earlier. This one here, when I'm going through the rotation, I'm entering the negative terminal of the voltage source, which means that I have to define it as negative 2 volts because it's a positive 2, but with respect to the proper direction. This one here, I'm following the direction of the current we defined for V2, so I'm calling it positive V2. And that's how I end up with this. 0 is the sum. And then here I have a negative V1, I have a negative 2, and a positive V2. And that's where I got that equation right here from, was that.
Okay, thanks, Alex.
No problem. I hope that answers questions. Okay. So the next one we're going to do here, I'm going to move over to a mesh analysis problem, I think, because I've got another supernode, but I don't think, is everybody okay with supernodes? Does anybody want to do another supernode problem before we move on? Okay, so then I will move on to a mesh analysis problem. So mesh analysis, we're going to use KVL now. it's kind of counterintuitive. When we're solving for node voltages, typically KCL, so Kirchhoff's current law, is more effective for doing that. Whereas when we're solving for branch currents, the voltage law is often more effective. These aren't rules, like definite rules, but that's generally what we see when we're solving these problems. So that's something just to think about as well. When you have to solve for currents, typically the voltage law is going to help more. And for nodes, typically the current law will help more. Okay, so I have two problems here with mesh analysis, so we'll do them both. We'll start with this one here. This one here is more, it's kind of like an introduction to it, and then the other one we get a little more involved. So this one here, I have this circuit here. I don't know what I'm doing to select it. So one important thing about mesh analysis, we've talked about it before. Just to review, what we do is we define two currents that are called mesh currents for each closed loop. And then we use those to determine the real currents. Now, when I say determine the real currents, I do actually mean that the mesh currents don't really exist. They're just a tool we use. Like if we go into the lab, you can't measure a mesh current. Well, generally speaking. There are instances where the mesh current will be the real current, but if it's not, then it's not measurable. It's just a tool we're using for analysis. Does that make sense to everyone? These problems are coming from a different textbook. I don't remember the name of the textbook I took them out of. I borrowed it from Dr. Mirasani like forever ago, but it's a very old circuit analysis textbook. I can try and find it for you guys if you want. What is it? I think it's Sadhguru is the author's name. You guys may have used it for circuit theory. It was one that I had used when it was similar to the one that I had used when I took that course. But it's not the Cedra Smith textbook or the Hurst either. I believe it's Matthew Sadhguru is his name. Yeah, that could be him, Matthew Sadhguru. I'm probably not saying that properly either, but you know, I tried. Okay, so we move on. We get a mesh. I can't believe that one worked. So, I spoke too soon. Okay, so I1 and I2. Let me try that again, because I seem to have just kind of written on top of everything. And then two. Okay. So you have to, well, I don't know that you have to. I usually do define the currents going in the same direction. I just like to be consistent with how I do them. I don't know if it's a rule or not. So maybe not, I wouldn't call it rule, but generally I do. It could be a rule. Again, I'm not 100% sure on that, but I always have. So it works that way. So define them in the same direction just to keep yourself consistent. In my case, I usually like to go clockwise. You can go counterclockwise. It shouldn't matter as much as long as you are, again, consistent with your current directions. That is the most important point. So this problem here, we want to find the mesh currents. That's basically all we're doing. And then so I'm just going to show you how we find them. And then the next problem will show how we use them to find a real current. In this case, the mesh currents actually will exist because it'll be through here. Like this, there's a branch that has just I2 in it, and there's a branch that has just I1 in it. However, in the next problem, you'll find that there's a branch where the top resistor is It is 9. No, it is not any of those. 9. So in this case, we'll just solve the currents, I1 and I2, and then we'll see how we do it. So first thing, we're going to, again, like I said, it's going to be KVL, the voltage laws that we use when we're solving for these currents. So we're going to do a KVL in this I1, in the direction of I1, we're going to do a KVL just like we did with the supernode. So here's what we've got. We've got here KVL in mesh 1. How come when I want more room going downwards, it won't give it to me, but then it gives me it when I don't need it? Okay, so first thing we have is its voltages. This is not currents anymore that we're measuring. So we've got 0, because the sum is 0. And we use Ohm's law to determine the voltage, just like we use Ohm's law to determine the currents. So Ohm's law means current times resistance will give us voltage. So this one here is 2 times I1. Two times I1. This one here is 12. We have I1 flowing this way, and we have I2 flowing upward. So it's actually the difference of the two currents times the resistance. So 12 times I1 minus I2. Next one is this here. We just have I1 going through it, so it's going to be 4 times I1. And then we have that voltage source there. And that voltage source, we're entering the negative side. It keeps giving me this box. I don't even know what it is. So we have here, we're entering the negative side, so it's going to be a negative 36 volts. Okay, and that's our first equation. I'm going to simplify a little bit, so I'm just going to put the 12 into the brackets and then collect the terms, is basically all I'm doing. So 0 equals 18 times I1. 18 times I1 minus 12 I2 minus 36. That's going to be equation 1. Okay, so KVL at mesh 2. So what's happening there? I'll go back to the circuit. I'll explain what I did. I'll write it all out, and then I'll walk back up with it because it seems to be better if I do it that way for writing. Okay, so first we have this one here. It's 9 times I2 because it's going to go in the direction. We're entering the positive terminal of the voltage source, so that's positive 24. And then we'll have I2 times 3 for this one here. And then in this case, it's now 12 times I2 minus I1 because our direction of reference has changed. It's clockwise in this loop, which means that this one is positive and this one is the negative one. So I'll write all out what I just said. So 0 is the sum. 0 equals 9 times I2 plus 24 plus 3 times I2 plus 12 times I2 minus I1. So it's different than the first loop. Again, I'm going to collect some terms, and here's what I will end up with. 0 equals negative 12 times I1 plus 24 times I2 plus 24. That's equation 2. And now I'll scroll back up so you can see a little bit more of what we were doing there. Okay. Any questions? Oh, there's another. This tutorial is only an hour? Okay. I'll post, what I'll do is I'll post some solutions to some of these questions. If you guys want, I can stay till, like, if someone says they'll stay longer. If you want, I can stay if enough people want to, and then I'll also just post. I can post the solutions as well if you guys want. But I'm happy to sit around and answer questions if you guys need, because I'm here at my desk anyway. It doesn't really matter. It's up to you guys. Yeah, I'll post solutions for sure. So yeah, okay. So now I know for the future it's only an hour. Because I had an hour and a half of material plans, and then this thing slowed it down. I'll try and fix the driver's issue. It must be a driver issue, so I'll try and fix the writing pad for next time. Sorry about that, guys. Any questions before you guys go? Oh, write the solutions down? Yeah, I can give you guys the solutions for this one too real quick if you need, and I will post the solutions for this as well. So our answer ends up being that I2 is 0. And looks like I wrote I2 twice. And then I1 ends up being 2. So I2 is 0, I1 is 2 amps. I'll double check that because I think I accidentally wrote down I2 twice. But I will double check that, and I'll write it into the solutions for the that I'll post. Okay. I could have made a mistake in the math. Very, very possible. I will double check it before I post them. Okay. Yeah, no, I am not immune to mistakes. I warned you guys. So I'll double check it. All right. Everybody have a good weekend, and then you can look for the posted tutorial, and then I'll hopefully for the next time have all of this stuff fixed with the writing pad. All right, take care, everyone. The Texas circuit theorems initially on Blackboard. I can ask her about that for sure. Yep. All right.